Welcome to all our alumni joining us locally and internationally. For those who don't know me, I'm Udeshka Vijayawardhan. I'm the Alumni Engagement Manager for the Faculty of Science. It gives me a great pleasure to bring our alumni webinar series to showcase some of our fantastic researchers from the different schools in the Faculty of Science. Today, I've got representatives from the School of Physics joining me. We've got the head of school, Stefan. We've got our speakers, Kaye and Taïssa, Julia, a moderator, and Professor Daniel Price, who's the alumni liaison for the School of Physics joining in. Before we start, I'd like to acknowledge the traditional owners of our land that we're presenting on. And also, I'd like to welcome any members who are in the audience who are of Aboriginal and Indigenous backgrounds. I welcome all of you to the country and also pay respects to our elders, past and present. Just to give a brief overview, so Professor Stefan Meyer, head of School of Physics, will give a couple of minutes of an update on what the school is doing, and followed by a 30-minute presentation from Kaye and also Dr. Taïssa Danilovich. After that, we'll have about 20 minutes Q&A of a Q&A session, which gives you an opportunity to ask any questions from our fantastic researchers here today. Without taking time, I'd like to give a little bit of an introduction to Professor Stefan Meyer. So Stefan's joining us as the head of School of Physics today. And he has been previously working in, sorry, I've actually lost your notes, Stefan.
Yeah, that's fine. I can just do the
just
introduction.
If you'd like to, yes, give an introduction.
Excellent. Welcome everybody. It's a real pleasure to be here. It's my first alumni webinar, so I'm quite excited to see that so many of you have joined. So I'm originally from Germany, but spent most of my academic career in the United Kingdom at Imperial College London, and then joined Monash about 2 years ago as head of School of Physics and Astronomy. Yeah, we shouldn't forget we have astronomy as well. So let me, especially since on the panel we have 2 astronomers. So let me give you a very brief overview of where we are at with the school. Probably many of you might not have been on campus recently. So these are 2 photos that we took today. So we have survived the storm that went through Oakley last week. Those of you in Melbourne might have experienced it. So these are our 2 main buildings. So the left one here is the New Horizons Research Lab. We are mainly on the 1st floor here, and this is where most of our laboratories are. So our laboratory-based research, which is probably a quarter of the faculty to a third of the faculty that's actively supervising students and postdocs and in laboratories, they are mainly based here. And a big part of that is our ARC, Center of Excellence for Future Low Electronics, called FLEET. There's a lot of research on 2D materials there. And then our main building for staff and for teaching, you see here on the right, and hopefully some of you might still recognize that. So that's the School of Physics and Astronomy as of about nine years ago. So I joined, as I said, in 2022 as head of school. Our deputy head of school is Amanda Caracas, an astrophysicist, and we have put the school into a structure of 5 research groups. So overall, we are now 38 academics, and the main fields of research are quantum. So those are quantum materials, photonics, quantum information science, then imaging physics. So today the webinars are about imaging. So Kaye is part of the imaging physics group. She will tell you a little bit about that. We have astrophysics. That's where Taïssa is currently a DECRA fellow. It's a very, very prestigious junior research fellowship. So we're very pleased that she chose us as the host. And then we have a particle physics group, and very new as of 2 years ago, and I'm going to speak a little bit more about that. We have a group that's actually looking at physics of education research. We've been quite successful in the last couple of years. I've just put some of the main successes in here. So one of our new staff members, also actually from the Physics of Imaging, Amelia Liu, won the prestigious John Booker Medal of the Australian Academy of Science. As of 2 years ago, we also have 2 fellows. 2 of our members, Michael Führer and Joan Etheridge, are fellows of the Academy, and we have 2 researchers that are on the so-called Clarivet highly cited list. So these are researchers that are in the top 1% internationally in terms of citation. Outreach has always been a very important part of the school already for over a decade, and I'm very pleased to say that last year our efforts there got recognized with the Silver Pleiades Award. So before we come to the talks, I want to talk very briefly about education. So those of you that went through our bachelor recently will probably know that we very much believe in group-based learning, studying, and problem solving in order to give our students an experience that is really group-based. Yeah. So here you see some photos of that we also recently took of our study spaces. Yeah, so up here, these are our learning studios. So you see students learn mainly from each other with lecturers and TA assistants walking around. And this is now actually also rigorously supported as of about 1.5 years ago. We have a physics of education research group where we actually also do methodological research on what does it actually mean to learn physics and how can we best support the learning of students. And that's led by Anna Phillips, who joined us from Cornell. So maybe in one of the future webinars, we can actually also talk a little bit about education. But now that's enough for me. I just want to briefly introduce Daniel here. He is our alumni liaison. He's a professor in astrophysics, and he has great plans for being more engaging with all of you. So Daniel, if you want to say 1 or 2 words.
Just going to say welcome. This is our first mini event for Astro and Physics alumni. So I can see at least some names on the list that I recognize. I've been around Monash for quite a while, but not as long as some of the other people. So one of the ways that we're keeping in touch, I would just mention, is through a LinkedIn page. So if you're already on LinkedIn, or if you know what it is, then please look us up. We're the Physics and Astronomy, Monash Physics and Astronomy alumni. I believe you will get a link emailed after the webinar if you've registered but with an email address. So that's what we're trying to use as the main way of keeping in touch with physics and astronomy alumni specifically. So yeah, we hope to have some more in-person events as well. I mean, Udi's got some great plans also, but we're really trying to make an effort now to keep in touch with people a bit more actively, because our students benefit from it too.
Okay, so thanks, Daniel. And I think with that, it's back to you, Udi, and we can start.
Yes.
With
So thank you.
Our 2 great talks.
Yeah, thank you, Stefan and Daniel, both. Yes, School of Physics and Astronomy. Yes, that's something I missed overlooked. So we are now moving to the formal part where the presentation will start. So I'll just quickly introduce the moderator for this evening, Julia Chinkagrana. Julia, if you'd like to say hi. So Julia is joining us from the, well, she is a stellar astrophysicist, and she would be moderating this session. So Julia, if you'd like to take over the session from now, I'd leave it in your capable hands.
Sure, thanks, Udi. So before I introduce the speakers for tonight, I want to quickly cover some housekeeping. So as a reminder, each speaker is going to talk for 15 minutes, and then after the presentations, we're going to do a 15 to 20 minute Q&A with them. So during the talks, or whenever you think of questions you'd like to ask, please put them in the Q&A function in the toolbar at the bottom of your screen, not the chat. And I'll try and get through as many questions as time allows during the Q&A. So this evening, it is my great pleasure to introduce Associate Professor Kaye Morgan and Dr. Taïssa Danilovich. Kaye works to develop new methods of X-ray imaging. She uses both conventional and synchrotron X-ray sources for her experiments, making particular use of the Australian synchrotron, local to us in Clayton. Kaye applies these new X-ray imaging methods to medical problems in collaboration with radiologists, engineers, physiologists, and other medical professionals. So an example of this is the work for which she was awarded the 2023 Eureka Prize for Excellence in Interdisciplinary Scientific Research. For this, she was looking at how the movement of the lungs is affected by cystic fibrosis. Kaye has an incredibly impressive publication record and has been supported by a number of fellowships and grants. She's won over $15 million in funding from the Australian Research Council, the Victorian Endowment for Science, Knowledge and Innovation, and the Institute for Advanced Studies at the Technical University of Munich. Now, Taïssa has a slightly different imaging application, and that is of dying stars, particularly looking at the dust and the molecules that form around these stars during their death throes. She combines observations taken with various radio telescopes around the world, including the cutting-edge ALMA telescope array in Chile, with computational methods to determine how quickly stars that are similar to our sun end their lives and what sort of material they produce along the way. Dr. Danilovich's studies have taken her around the world. Prior to taking up a position at Monash as a DECRA Fellow funded by the Australian Research Council, she held 2 postdoctoral fellowships awarded by the Research Foundation Flanders in Belgium and completed her PhD in Sweden, funded by the Swedish Space Board. She's also operated telescopes in Chile, Spain, and Sweden. So without further ado, let's begin the talks. Kaye, please take it away.
Thank you, Julia. So I'm going to start with chapter 1, X-rays, how we can use X-ray imaging for good. So I think everybody will be familiar with an X-ray. It usually looks something like this. We see the bones and they're effectively casting a shadow, because X-rays, they can get through the fat and the muscles and the soft tissue, but they can't get through bone easily. So just like visible light can't get through us and so casts a shadow, the X-rays can't get through the bones. And so we get these really nice shadow images of the bone. We typically see it like this because X-ray radiography started with film, but actually it probably looks something more like this. So there's a shadow that's darker in both instances. But we can't see anything about the things that are surrounding the bone. So those muscles and the fat and the skin and all the organs like the lungs and the heart and the brain that aren't going to cast a shadow. So that's the research question that I'm trying to answer. How can we see these X-ray transparent objects? So I want to think about what we think about normally for transparent objects with visible light to start off with. So water is transparent. The light goes straight through it, doesn't cast a shadow. We don't really see it in the same way that we see all the other objects around us. But we can still tell that there's water in this swimming pool. We can see that there's these white lines that are kind of dancing around the bottom of the pool where the wave is focusing the light. We can also tell that there's water in this pool by looking at the tiles on the bottom of the pool and how they're distorted as the waves move over them, distorting the image that we see. And this kind of inspired the approach that we've been developing at Monash over the last decade. And so what we've been doing to try and see the transparent parts of the body is that we effectively put tiles at the bottom of the swimming pool. We effectively put some kind of grid pattern like the tiles, and then we look at how there are changes to that grid pattern from the transparent object, something like the lungs or the heart. And so you can see that some of these tiles as such, these little dots, are sometimes squashed together, sometimes spread out, sometimes a bit brighter, sometimes a bit darker. And I want to consider, first of all, just one individual dot. What could happen to that dot, and what would that tell us about the shape of the transparent object we want to see? So the first thing that could happen is that dot could be attenuated, and this is what happens in normal X-ray imaging. So that little tiny dot there could become dimmer, it could dim. And so that's a kind of a shadow. And we might think of that in the visible light sense as a glass of milk. We have this little beam of visible light going in, it's not going to make it out the other side very well, perhaps only a small fraction. And so we see this shadow image. And so if we look at how the dot dims, we'll get the kind of conventional X-ray image that we see here, where the bones show up really well. But the dots also have some other dance moves. They might drift off to the side, a kind of side step. And what's happening in that case is that actually the beam has been refracted. It's changed the direction that it's heading. And so this is kind of like a glass of water. It's transparent. It's not giving us a shadow, but it is changing the path of the X-rays or of the visible light. And so the further we move away from the object, the more we'll see that little dot drift away from its original position. And if we do that, we'll get an image that looks like this, where if the image is darker, it effectively means the dot drifted to the left. And if it's brighter, the dot drifted to the right. And suddenly we can see the lungs in excellent detail. We can see these airways that are going down to them and the shape of each part of the lungs. But there's one more dance move that the dot has, and that is it can diffuse or kind of spread out. And so this could happen when a beam of X-rays goes through something that has a lot of tiny things in there. So bubbles, for example, in a glass of water. And so as the X-ray beam goes through, it kind of bounces back and forth like a pinball through these bubbles. And it means that you get some heading out in slightly different directions to the others, and the beam kind of spreads out the further away we are from the object. And if we do this at every point across what we want to image, we get an image that we call a dark field image. And so here we see the lungs, but not the airways. And that's because the lungs are made up of lots of tiny little air sacs, which are diffusing the X-ray beam that goes through. So we could take an image with one dot, but it's not going to be very efficient scanning across the whole of the patient. So let's put a whole array of dots across there. Then we can look at how each dot dims to get the attenuation image, how they drift to get this phase image, and how they diffuse to get the dark field image. And if we're collecting all this information all at the same time, we can really track every part of the sample by looking at these dancing dots. And so Ying Hao, who's a PhD student in my group, has been looking at particularly the diffusion, how we can get information about those tiny little structures, for example, in the lungs. And so we can capture an X-ray movie even to look at how that changes through the breath. You can see the lungs get a little bit dimmer when they're most full of air. And so we can try and extract information then about how healthy those lungs are from how much that value changes. So this is really exciting, but as physicists, we're never satisfied and we want more. So the question that we've been looking at in the last 2 years is, could we do this without having a whole array of dots, without having tiles in the bottom of the swimming pool? Could we still figure out the shape of the water or the transparent objects in the body if we just kind of pack in lots and lots of tiny X-ray beams such that we're effectively just spreading light over the whole object that we want to image? So all these dots are going to overlap each other. The image that we'll see is going to be a combination of all three of these effects. And it will look something like this. So if we zoom in, we can see the dimming in terms of the bones shows up still quite clearly. We can see these phase shift, the drifting, as a kind of focusing of the light. So each of those little air sacs in the lungs is kind of acting like a lens and focusing the light into these bright dots here. The other thing is the dark field. Can we see this in this image? And this is a question that hasn't really been addressed until very recently. And we believe that we actually can. So we've got an image of a piece of coal here where we've just thrown light at it. There's no little beamlets. And we can see that some parts of it are quite absorbing. So it's quite dark here from the attenuation, so the dimming of the beamlets. We see these kind of bright lines around the outside and these kind of focused little dots. So we see those phase effects or the drifting. And we can also see that some parts are kind of blurrier than others. And so we believe this is from the really tiny structures that are inside the coal that are bouncing the beam around and kind of washing out the image that we would otherwise see. So if there was none of these tiny structures, it would be quite sharp everywhere. But because they've kind of bounced the light around and diffused it out, we've got this kind of blurry area here. And so PhD students Thomas Leatham and Giannis Allers have been developing new algorithms that we can take one of these images and extract all three of those new X-ray imaging modalities. To do this, they can't track the beams, so they need some kind of model. And the model came about a couple of years ago from discussions with myself and David Paganin. So this equation is known as the Fokker-Planck equation. It's used in a number of different areas of physics and beyond, but we adapted it to describe what happens to the X-rays as they pass through the air between the patient and the X-ray camera. So effectively, I'll just go over it very quickly for those who are interested in equations. It's saying what's happening to the X-ray intensity or how bright a certain part of the image is as we change the distance away from the sample. So as we change this Z, how does the brightness change? And this first term will tell us about the drifts in the X-ray beamlets, or in fact, just the uniform illumination, the throwing light at the whole thing. And the second term will tell us about the diffusion or the X-ray dark field signal. And we can also extend this equation into 2 dimensions to even look at a directional dark field signal, which I'll leave for the question time. So they've developed these new methods, but the question is, where can we do these? Where are these images coming from? So I wanted to show you one of the main experimental facilities that we use to perform these new kinds of X-ray imaging. So this is the Australian synchrotron. It's just across the road from Monash University, the only synchrotron in Australia and the largest in the Southern Hemisphere. So this facility, it produces X-rays, and it does that by accelerating electrons to almost the speed of light. And they pass in a circle within this big tunnel that you can kind of see underneath here. Every time the electrons turn a corner to make a circle, they give off light, very bright light, and that can include X-rays. And so there's these whole series of experiments at every corner of the circle, if you like, to collect the light and try doing different things with it. So this is the microcomputed tomography beamline that we use. This big blue room is made of lead to keep us safe from the bright X-rays. And so in here we would set up the things that we need. So we'd put the object that we want to image. We might also include a grid pattern to make those tiles on the bottom of the pool effectively. And then we have an X-ray camera that Giannis is moving back here to allow the X-rays to really drift and diffuse before they are recorded by the camera. There's also a lot of motorized stages. So here we see the camera moving from one lens to another to zoom in on a particular part of the sample. So once we've set up the experiment inside the hutch, then we head over to a control room where we can monitor everything that's happening inside, and we can control the camera to capture some X-ray images. The other beamline we use is down a very long tunnel, and that's because it's the largest beam at the Australian synchrotron, the imaging and medical beamline. And so it also has a very large blue room in which we conduct the imaging. And so this allows us to image very large objects, unlike the micro CT beamline. And there's these robots usually reserved for making cars that we use to move what we want to image around. So this can even lift a tree up and down to capture images, for example. There's also the space to have a very long distance between the sample and the X-ray camera, so we can really see that drift and diffusion of the X-rays. So once it's all set up, then we close up and we head out to a control room just like MCT. So this is kind of step 1 in our research, but what we'd really like to do is move these techniques to small compact X-ray sources to be able to install them in hospitals everywhere. So one possibility is the Munich compact light source that I used during a previous fellowship, where they've kind of compacted a synchrotron down to the size of a room, which really makes it compatible with installation in a hospital. So it would be great to have something like that. Where can we use this X-ray imaging? So the obvious first example is radiology, imaging the body to try and pick up disease and monitor any progression. So this is a conventional image of a lung. At the Australian synchrotron, using these phase techniques, we can get an image that looks like this. Hopefully you can see that the details are much sharper, that we can see features that are invisible with the kind of conventional X-ray. And then we get these really kind of nicely defined vessels in the lungs, and also these kind of tumour models. We can see quite a large one here and also a smaller one on the other side. But when they get really small, we really have to look at them in 3D. And so we combine phase contrast with computed tomography to be able to see an entire volume and kind of move down through the body to see and isolate each part of the anatomy. And so this is part of a large project looking at can we get phase contrast lung imaging to detect cancer into hospitals from the group that we see along the bottom here. We can also use these techniques to better understand how the body works and how we can look after it. So one type of imaging we do, we look at how the lungs move during the breath. And we also look at that from all angles so that we can reconstruct a 3D movie of how the lung is moving. And so this enables us to see if there's a particular part of the lung that's not inflating properly, which is perhaps affected by disease. And so we can get really sensitive local measurements of lung health. And so we're using this in a couple of studies. So looking at what happens to your lungs when you're on a ventilator for a long time and how to avoid injury. And also to look at how treatments are helping the health of the lungs in the case of lung infections. This has also been developed by the company 4D Medical for clinical imaging. We can also look at treatment effect at a very local scale. So we can zoom in on the surface of the airway here. And we see here a change in the hydration of the airway in response to a new treatment for cystic fibrosis lung disease that's been developed by my collaborators at the University of Adelaide. We can also see when the airway surface is rehydrated, that any inhaled dust or debris moves up the lungs towards the mouth so that we don't have any accumulation of debris in the lungs. And so we can zoom right in and actually see that happening. This can also be an issue in that if we deliver a treatment to the lungs, it doesn't always stay there. Sometimes it's cleared along with the debris. So one other area that we've been exploring is how can we keep the treatment at the right location? And so we've been looking at doing that using magnetic nanoparticles that have the treatment attached to them, and then placing a magnet outside the neck to hold those magnetic particles at a particular treatment site. We can also look at moving the magnet along the airway surface to see how those particles move in reaction. We see with the magnetic field lines that we can actually make them walk down the airway towards the lungs where they can have maximum effect. Phase and dark field imaging has also been used in kind of looking at museum samples. So this is an example here of one of Australia's smallest marsupials, the honey possum. And my collaborators, Justin Adams and Lucy Costello, were interested in understanding the anatomy and function of this very, very small creature. And so they had a sample from the museum, a small honey possum, and we CT'd using the extra phase effects. And you can see that instead of only seeing the bones like we would normally see in a CT, we also see the fur, we see the brain, we see the heart, we see the lungs, and Lucy was able to pick out all of these organs from this 3D image. The other thing that we picked up, which maybe you can see, is there was actually some babies in the pouch, which I didn't know about when it first went in for imaging. So quite a discovery. So where else can this be used? We've only put a couple of things in front of the beam, sometimes a bit random, and we get such new and complementary information. So here we see some headphones and a water bottle. In the normal X-ray, we see all the metal parts, but then in the dark field, we see where there's foam, where there's lots of little structures to bounce that X-ray beam around. And so the features that are coming out of these new kind of images are things that haven't been seen with X-rays before. So I think there's numerous possibilities for where these techniques can be employed in the future. And with that, I'll thank you for your attention, and I'm going to pass over to Taïssa for chapter 2.
Thanks, Kaye. So I'm going to talk to you about how we can use imaging to understand the very big by imaging the very small. And what I'll be focusing on mainly is dying stars. So that's the deaths of stars similar to our sun. And the sun is something that you're all probably pretty familiar with. So here is a picture of the sun. It was quite hot today in Melbourne, really shining down on us. And I'm sure you're all aware that the sun is a lot bigger than the Earth. In this image, I've put them to scale. So the Earth is that much smaller than the sun. Or to put it another way, the diameter of the sun is about 100 times the diameter of the Earth. And of course, the sun looks relatively small in the sky above us because it's quite far away. How far away is the sun? Well, that's about 100 times the diameter of the sun between the sun and the Earth. So the sun is a very big star by our Earth standards. It's about average in the scale of the galaxy. The average mass of a star in the galaxy is about 90% that of the sun. So the sun is pretty close to average. Right now, the sun is shining because of fusion that's happening inside the core. So this is mainly hydrogen fusing into helium. That produces a lot of energy and that makes the sun shine. But even though the sun is big, it's not infinite, and eventually it will run out of fuel. And at that point, it will start to change. So it will begin what we call an evolutionary journey. So how will the star that is our sun change? Well, starting from its current state, which we call the main sequence, once it runs out of fuel in its core, once it runs out of hydrogen, I should say, it will fuse helium for a little while longer. And at that point, it will expand a lot. It'll become what we call a red giant star. Eventually, it will also run out of helium to fuse in its core, and it will become what we call an AGB star, which stands for asymptotic giant branch and is not really like the most exciting name, but it is unfortunately the name we're stuck with. AGB stars are very big, so by the time the sun reaches this stage, it'll have expanded to 100 or several hundred times its current size, which does mean that yes, it will engulf the Earth when this happens. During the AGB phase, it's a very sort of dynamic phase that the star goes through for about 100,000 years. And it's dynamic because the star has expanded so much, its outer layers are not very strongly attached. So the gravity is much weaker than it is at the surface of the sun currently. And the outer layers of the star will be thrown off into space. And this happens sort of gradually, and eventually all of the outer layers will be gone, leaving behind a white dwarf, which was once the core of the star. And all the material that was thrown off will form a planetary nebula like we see on the side of this image. So planetary nebulae are quite pretty, but the main focus of my talk will be on AGB stars. So I said that these stars throw off their outer layers. This is a lot of material that's mainly gas, and a lot of that gas is in molecular form. Once the gas moves a little bit away from the star, some of it forms dust, but most importantly, it all eventually flows back out into the universe. So I talked about hydrogen and helium fusion inside the star while it's similar to our sun, and in the next stage, once it's an AGB star, there are still some nuclear reactions happening, something we call nucleosynthesis, where new elements are being created, and it's a little bit more unusual elements. These stars create about half the carbon in the universe overall, and about half of sort of other miscellaneous heavy elements. And once they're thrown out into the universe, or thrown out into space around the star, these new elements will eventually go on to form the next generation of stars and planets. So these stars contribute to the enrichment of the universe, and by making the material in the universe have more heavier elements in it. So what I mostly study is small molecules that form around these dying stars. So then the question is, molecules, they're very small, they're made up of, two or a few atoms. So how can we see them when they're, far away out in space? And the answer is using the ALMA telescope or other telescopes like it. So ALMA is a big telescope in Chile. It's made up of 66 radio dishes, as you can see in this image, showing some of them. They are spread over 16 kilometers on the Chacnantor Plateau in the Atacama Desert. So this is in Chile. The plateau was chosen because it is a large plateau. We can spread out the dishes, making them work together so that we can image things in very high resolution. Because when the telescopes are spread out like this, they can act as though they're one giant telescope using, some computational magic to link them all together. And that's a lot easier than having a one giant telescope. I mean, we can't really build one satellite dish that's 16 kilometers in size. That's just not technologically feasible. This telescope is also in the desert, 5 kilometers above sea level. So at that height, the density of the atmosphere is about half the density of the atmosphere that we experience at sea level. So there's a lot less atmosphere to get in the way of our imaging. And okay, I've explained what the telescope is, but how does it actually image things? Well, that's by looking at small changes in energy that molecules go through. So a molecule might be, floating in space near a star, whatever, and it can change its energy either by absorbing a photon, from a nearby star, for example, and moving into what we call a higher energy state, or it can cool down a little bit and then it emits a photon and moves into a lower energy state. And then the ALMA telescope can collect all of these photons and, put them together, a bit of computational work in the background, and we get some lovely images. So for example, here are some images that were taken as part of the Atomium large program, which is, well, a large observational program that was conducted with ALMA. In this image, we're seeing carbon monoxide gas, so that's CO, and that's the way it's shown in the image here. We've got the blue colors show gas that's coming towards us, and the red colors show gas that's moving away from us, and the white or sort of greenish white in between is gas that's just moving sideways, so not towards or away from us. As we can see here, there are lots of interesting and unusual structures that we can see in the gas. And one of the things that I'm working on is understanding why we get these interesting structures in the gas. So these are all stars that started off similar to our sun, but are now going through this AGB phase, throwing off their outer layers. But they're not doing it smoothly, and we want to know why. So to begin to understand this, I studied this one particular star here, W Aquilae, in my latest paper and several other papers, and I'm going to talk a little bit more about that now. So in this new image that I've shown up, here's a bigger version of it. This is just showing the carbon monoxide gas sort of moving outwards from the star, sort of near the center of the star, moving outwards. So this star is called W Aquilae. It's not actually one star, it's two stars. There's the dying star, the AGB star, which is what's throwing off all the gas. And then there's a sun-like star orbiting it. So in this particular image, both stars are in this bright central bit, and they're both actually smaller than a pixel, so we can't see them in this image. But all these shapes that we see, these arcs around the stars, those were formed because of gravitational interactions between the two stars. So looking at this image, that's all a little bit complex. It's hard to determine exactly what's going on, but we can see that there are some structures there. We can also see that the gas is a lot brighter close to the stars, and that's because the gas is expanding outwards. So close to the star, it's a lot denser, and further out, it's less dense. And then when it's less dense, it's harder for us to detect because it's spread out. There are fewer molecules, they're emitting less light, they're a bit harder to see. So this is carbon monoxide gas around this star, but we can also look at other molecules. And so I'll show you one other molecule, and that's what we call SiN, or silicon nitride. This is a slightly unusual molecule. It hasn't actually been detected for very many stars. So when I saw it in the emission spectrum for W Aquilae, I was interested. I wanted to know what it could tell us. I mean, it's a little bit my thing, finding the unusual molecules in space or around these stars, and trying to understand what different things different molecules can tell us. So when I imaged SiN, which is shown here on the right, I was surprised that it's kind of a triangle and like off to one side. So most molecules either show some of the structures that we see in CO, but more confined. CO is a very sturdy molecule. It exists quite far from the star. Most other molecules are destroyed more quickly. So mostly we see kind of roundish blobs near the star. But in this case, we get a blobby triangle, and that was a bit strange. Looking into it a little bit further, I learned that this molecule, SIN, needs UV light to form. So basically UV light affects other molecules, which then go on to form a chain reaction that eventually produces SIN. So, okay, fine. Well, we've got a sun-like star that produces UV, right? We experience that on Earth. We go outside without sunscreen, we feel the pain of UV. But in this case, the sun-like star is on the wrong side of the star compared with the SIN emission. So how did that happen? And what's going on? So delving into astrochemistry a little bit deeper. So astrochemistry is the study of what kind of chemical reactions happen in space. We found out that right now, the sun-like star is far enough from the dying star that the gas that it's near is not very dense. So while UV photons from that star might collide with a few molecules and it might destroy them, those molecules, or those now atoms, don't collide with very much. There's not really a chain reaction. Everything is just too spread out. So this kind of points a bit to the answer. If at some point the sun-like star was close to the dying star, in the dense gas close to that star, then these chemical reactions could take place. And that was the answer we came up with, which I've sort of illustrated in this schematic. So this is looking down on the orbit between the two stars, which it turns out is very elliptical. So the Earth's orbit around the sun is almost a perfect circle. It's not quite perfect, but there is not a significant difference in the distance between the Earth and the sun over a year. That is not the case for the two stars in the W Aquila system. So I've drawn this diagram to put the AGB star, the dying star, not moving as the red star in this diagram. And basically what we worked out happens is as the sun-like star gets close to the dense inner region and passes through that dense inner region, it leaves behind basically a trail of destruction caused by its UV light. So molecules destroyed, atoms ionized, that sort of thing. All of these are now in this dense region where various chemical reactions can happen very quickly. Molecules are bumping into each other much more often, so SIN can form. The star then moves on along its orbit, which the whole orbit takes over 1,000 years to complete, so it's not very quick, but the time while it's swinging around the AGB star is quick. And then what was the path of destruction formed SIN and a few other molecules and expanded outwards, along with just all the other gas that's expanding outwards around this dying star. So now, when we observe the star, it's a lot further along in its orbit, and we can calculate from the observations that this path of destruction, this imprint of the close passage of the two stars happened around 200 years ago. So using that and a few other observations, we were able to actually constrain this orbit. So we started off this project just knowing the current separation between the two stars, and we ended up understanding the entire orbit and finding out that it was an unusual and very elliptical orbit. And this was only made possible by being able to image different molecules, and in particular this unusual molecule SIN. So just to summarize quickly, when stars like the sun reach the end of their lives, they become really big, hundreds of times bigger than their current size. They then throw off their outer layers, which create a lot of molecules and dust. And we can observe these molecules and the dust using radio telescopes. And then we can even use observations of molecules to understand the orbits of binary stars and systems. Okay, thank you. That's my presentation.
Thanks, Taïssa. So with that, we'll begin the Q&A part of the session. So I'm going to give a couple of minutes to everyone to hurriedly type out your questions that you've been dying to ask. And I've got one myself. So Kaye, you talked a little bit about going to the synchrotron to capture these new kinds of X-ray images. Is it possible to capture these kinds of X-rays with normal sources, or is there something particularly special about the synchrotron sources of X-rays?
An excellent question. I kind of glossed over that part. So the synchrotron provides us with two key advantages. The X-rays that we get from there are all the same energy, which means that we can make them interfere really well, like if we've got light that's all the same color. And so the synchrotron gives us really exactly one color. We can do some tricks with conventional X-ray sources that get us closer to that, and we can still get quite nice images from that. The other thing the synchrotron gives us is what we call very coherent light, in that all of the wave fronts are really kind of flat. So like the waves coming in from the ocean. Whereas a normal X-ray source would give us kind of just choppy water. So we can make the normal X-ray source look a bit more like a synchrotron if we put a really tiny pinhole in front of it, so that all that light that's coming out kind of comes out in waves that are a little bit more ordered. So we can see how the sample then changes the direction that they're going. So with just your conventional X-ray source, it's quite challenging, but there's these kind of sources in the middle that are coming along that either have a pinhole in front of them or a very small area, like this compact synchrotron that I mentioned, or a micro focus source. So we're kind of bridging the gap now with some of these new sources. And also some of the maths we're hoping will help us out with these new physics approaches to do the same thing with normal X-ray sources. Yeah.
Awesome. And when you say mini synchrotron, are you talking about literally a smaller miniature version of the synchrotron? Is it using similar kind of sources? Like, how are you going to get it into one room?
Yeah. So the kind of compact synchrotron, it sends electrons into an orbit similar to the synchrotron, but this time it's about the size of your kitchen table instead of the size of the MCG. So much more compact. And then instead of using magnets to make the electrons turn, the electrons collide with a laser, and the laser is electromagnetic light. So it looks like a really tiny magnet. And so as the electrons hit the laser light, then they produce these really coherent single energy X-rays that we need. So there's just one that's in the world at the moment in Munich, and there's a couple others that are in development. But it's certainly something that we'd love to have here at Monash to help bridge the gap from the synchrotron to the hospitals.
Lovely, thanks. So Taïssa, you mentioned dust around dying stars. What sort of dust is this? Is this the kind of dust we're familiar with?
Yes and no. There's actually two different types of dust that form, which can either be oxygen-rich or carbon-rich. And the carbon-rich dust is almost exactly like the kind of soot you might find in your fireplace when everything's burnt and there's just some black stuff left over. So mainly just made out of carbon. The oxygen-rich dust is what we call silicate dust, and that's really similar to sand, actually. So the parts of sand that are more like ground up little bits of quartz, not the parts that are like seashells. There's no seashells in space probably, but it's very similar to sand. So we're trying to understand how both of these different types of dust in slightly different environments can have very similar effects on like when they sort of fly away from the dying stars.
And do all AGBs have both carbon-rich and oxygen-rich dust, or what might be the reason that we have the different types?
Yeah, great question. So actually the way it works is that all stars start off oxygen-rich. Our sun will become an oxygen-rich AGB star. It's oxygen-rich right now. It's just that's not a very significant feature of it. But this means that there's a lot of spare oxygen floating around, and silicon is another element that's quite common. So they can bond together and they can make that dust. The actual chemical formula of the dust is slightly more complicated than that. But I mentioned earlier that inside these stars, new elements are being formed, and one of those elements is carbon. So as the star sort of stays in this AGB phase for longer, more carbon is brought up to the surface. And then when it's flung out, it eventually becomes a carbon-rich star instead of an oxygen-rich star, once basically there's more carbon than oxygen. And at that point, carbon really dominates the chemistry. So we get a lot more carbon dust forming, and we get some weird carbon molecules forming as well.
So thank you. So Well, let's have a look. Beautiful. We have a question from Linda. Will the SKA be helpful in studying AGB stars? That's a great question. Would infrared astronomy, as available with JWST, help?
Yeah, great question. So the SKA is looking at really long wavelengths. So at the moment, that's not the area I have that much expertise in, but I am excited to try and use the SKA to see what we can see, because there are some molecules that have very low frequency transitions that right now we can't observe very easily. To get the sort of resolution that we need to study individual stars, we need the power of the SKA with all the dishes giving us higher resolution, because there's this relationship in just the physics of light where the higher your frequency, so the shorter your wavelength, the higher the resolution is if you're looking with sort of the same size telescope. So if you look with very long wavelengths, which is what the SKA will be doing, the resolution, if you had sort of a similar sized radio dish to ALMA, which is at the high end of the radio frequency range, the resolution would be a lot smaller. So the SKA is going to be a much larger array, and that will let us study these things in more detail, and also in sort of enough detail to pick out individual stars, which is something that's not really possible at those really low frequencies right now. And the JWST is absolutely useful for studying AGB stars, but it's very sensitive. And right now, it's a bit of a challenge to study the same stars that we study in the radio because they're so bright in the infrared. They're some of the brightest objects in the infrared sky.
Awesome. So before I go, we've got another astronomy question. Before I ask that one, I want to throw one back to Kaye. So I want to know, is there something, an object or a particular medical issue that if you had 10 years of unlimited funding and unlimited PhD students that you'd love to keep working on?
Sure, yeah. Many, I would say. I think probably the one where we're most focused, and hopefully we can make progress in the next decade, is detecting cancers earlier. So they're X-ray transparent, and so to be able to get that extra information, the earlier you can find a cancer, the better you can treat it. So that's the aim.
Awesome. All right. So I have another AGB question. Maria asks, may I ask what other parameters can be determined by studying or identifying molecules and dust in binary star systems?
Yeah, absolutely. So by default, one of the things that we want to do first is understand how quickly these stars are losing material. So how quickly they're throwing mass off into the galaxy around them, because that lets us understand how long they will live and helps us understand their sort of entire evolutionary trajectories. And we can also study other molecules. So for example, water is a very common molecule around the oxygen-rich stars since it's H2O. And we can use isotopes of oxygen inside the water molecules. So the most common oxygen is 16O, but there's also 17O and 18O. And when we study these, we can use them to find out the initial mass of the star then, which also helps us understand sort of evolutionary journey and how different stars of different masses end their lives.
Very exciting. So we probably have time for one more question. I'm going to throw this back to Kaye. When you're doing the dark field imaging with the grid, what type of grid resolution do you need and how is it made?
So it depends on the scale. So for the largest area imaging, we have used a geological sieve. So you can get very precise sieves for getting one size dust from another. And so they go down to 25 micron holes. And so they're made of stainless steel, which is very absorbing. So it gives us this really nice grid pattern. If we go to an even smaller scale, we can use what's effectively an array of tiny lenses, which actually focuses the light into the grid pattern rather than kind of blocking out the light. And those ones are made of silicon, and it's made using lithography in a specialist lab where they put layer upon layer of exposing with a particular light and then depositing in a material, and a lot more involved than buying an $80 geological sieve online. So depends on the scale.
Well, that's probably all the time we have time for. Thank you very much again, Associate Professor Morgan and Dr. Danilovich. I'm going to pass it back to you, Rudy.
Thank you very much, Julia. Fantastic presentations from Professor Morgan and Dr. Danilovich. So thank you very much. And Julia, thank you for being a great moderator for tonight. For all our alumni who's joining today to listen to this webinar, I'd like to thank you. And I will be sharing this the recording of the webinar with you to share with your colleagues or your friends if you're interested in sharing it. I will also ask all of you to provide us some feedback so that we can continue to improve our webinar offerings and also events, etc., for our alumni and make it much more relevant for all of you. So thank you for taking the time, and thank you, Professor Daniel Price. He is the alumni liaison for the School of Physics. So if you're intending to do any reunions, etc., please do reach out to him. And we certainly can get everyone together. That's the hope, and I hope that the webinar series is quite informative, and we continue it one for each school every couple of months. So the next webinar that's coming up will be from the School of Biology. It's around the use of viruses to actually help with antibacterial resistance and how we go about doing the research for that. So stay tuned, everybody, and have a great evening. So thank you all.